Hello everybody and welcome back to the Automata and Formal Languages class and video lectures. In this lecture, in this unit, we will be covering some fundamental concepts in the mathematical proofs, and I will start this learning unit with the concepts of Boolean logic, and then we go through what mathematical notations, definitions, theorems, and proofs are, and how you could strategize in terms of getting some getting to prove a special mathematical statement, which effectively we call them theorems, and so forth. So let's start our or rather continue our work on the mathematical notations. One of the important things in terms of mathematical statements is that with each statement that we talk about mathematically, since everything needs to be completely defined and formalized for us to be able to make sense of it, we would have to have a architecture, a mechanism to be able to evaluate the truth of these statements, and this basically relies on the Boolean logic. It is a mathematical system that's built around two values, true and false. And although it was originally pure mathematics, this system of logic is now considered to be the foundations of all of the electronic devices and computer design, because in terms of electronics, the state of a unit of electricity could be considered as either having electricity or not. So therefore, a switch may be on or off. And so that is the easiest way to electronically represent the logic. And that's why Boolean logic has actually become a very, very important component of the design of the electronics devices and computer systems. However, throughout this course, we generally rely on Boolean logic as a means of evaluating a statement, a mathematical statement, or understand what if a statement can be logically derived from another or not. So the two statements that we talk about, the true and false, are basically your Boolean logic or Boolean values. So in the case of basically Boolean representations, true usually represents the value 1 and false represents the value 0. So we use true and false, or true and 1, and 0 and false interchangeably, as we discuss in this class. So basically, when we talk about Boolean values, we talk about the one out of the two possibilities that may be out there. And so in terms of propositions, in terms of the truth of statements, logically, if a statement is true, it's one possibility, and if it's false, it's then at least the other possibility out of the two. We use Boolean operations or Boolean operators to manipulate the logical values of multiple statements. And so in the majority of this course, we basically rely on these 5 Boolean combinations, although these are not the only ones. And also, in fact, all of these Boolean combinations or Boolean operations can be represented by only not and operator. So these are Boolean operations. Boolean operations are binary also operations, in that they take two operands and they combine the logic of those operands together to give you one value. The simplest one of these operations is the not operation. So, and we represent it either with this statement or with just a tilde, and both of these are the not operation, or also we call them the negation operation. What does this mean? It means that if you have a operand p, a logical statement, a Boolean value, and then you negate it, then the not of p is going to be basically switching the states. So if p was 0, then the not of p will be not of 0, which will be 1. If p was 1, then the not of 1 will be 0. So it basically swaps your logic. The next operation I want to talk about is conjunction, or AND. We also call this a conjunction operator. What this does is that it takes the logic of the content of two values, two statements, and ANDs them with each other, and it's going to be equal to true if both of them were true. Otherwise, it's going to be false. So if you have a statement P and statement Q, then P and Q is going to be true if both were true. Otherwise, it will be false. Contrary to this, we have the disjunction operation. It also is represented with the OR statement. So, and it's this upward V. So the AND operation, or the conjunction, is the backwards V symbol, and the upwards V as your disjunction. So if you have P and Q are two statements, two propositions, then P or Q is going to be true if at least one was true. If at least one of them is a true statement. Okay, so basically, for example, a statement could be today is Sunday, and another statement could be today is rainy. So this statement, if you use the disjunction of the two, today is Sunday or today is raining, it will be true if either one of the two or both are true. The conjunction is true when both of the statements are true. So for example, today is Sunday and today is rainy. This is true only if when you have Sunday and that it is raining. So if it's Sunday but it's not rainy, or if it's not Sunday but it's raining, or if it's not Sunday and it's not raining, then your statements will be false. So conjunction is true when both statements are true. Disjunction is true when at least one of the two statements are true. The next operation that I want to talk about is the exclusive OR operation, or the XOR operation. We represent it with the symbol cross and O. So a circle with a plus inside of it, it represents XOR. So it's called exclusive OR. So exclusive OR is going to be, so if you have P and Q, the P XOR Q is true if one and only one of them is true. Notice with OR, it could be true if both of them were true. But with exclusive OR, and that's why we call it exclusive OR, it excludes the case that both are true. So the exclusive OR is going to be true if both of the statements are true. For example, if I say today is rainy, today is Sunday, two statements, two propositions, the exclusive OR of today is rainy, exclusive OR today is Sunday, is going to be true if it is Sunday but it's not raining, or if it is raining but it's not Sunday. So So that's effectively your exclusion of both cases. The negation of the P exclusive or Q, it's basically true if one and only one of them is true. The negation of this is what we call the equivalence. So the equivalence statement, I probably should have made another bullet here. It's called the equivalence operator, or the equality operator, is true if both of the statements have the same value, meaning if one is false, the other to be false, and if one is true, the other to be true, then the result will be true, otherwise it will be false. So if you have P and Q, then P equal Q is going to be true if P and Q have the same value, or have the same Boolean value. Right? So if P was false and Q was false, then P equal Q is true. If P was true and Q was false, then P equal Q will be false. So basically, the equality is the negation of the exclusive OR. So these two, the relationship between these two is that P X or Q is going to be effectively the NOT of P equal Q. And finally is the special kind of operator. We call it the implication operator. This is a conditional operator, basically, if you want to think about it. So I'm going to basically I'm going to get this and just take it out and talk about it separately. So P implies Q is a special kind of operator. This is going to be true if or rather, let's talk about it the other way. It's going to be false if P is true but Q is false. Okay, so in other words, if P is false, then it implies anything. So if P were to be false, or your assumption in this implication is false, either one of the contents, either one of the Boolean values for the Q will be effectively implied. So from a false, you can imply either false or true. And but if P or if your assumption is true, then you can only the truth statement can only imply truth. And this implication is really important, because this is at the heart of deriving mathematical proofs. Effectively, you can think of the implication as this: if P, then Q. And a lot of, so these two are basically equivalent. Another way to say this is that P implies Q. And a lot of these statements, mathematical statements that we talk about, we basically start from something, and then we try to see if that implies another thing, if that other thing implies the other thing, if that other thing implies the other thing, and build our empire of mathematical proofs. And a lot of those proofs are going to be in this form. So effectively, you'd start with some assumption, and if the assumption was true, which you should validate and make sure that the assumption is true, then go through a sequence of mathematical steps to try to derive another statement that would help you with your proofs. So this has a very special importance for us, this implication. Another measure of this implication, or another operation that's a bidirectional implication, which we represented with an arrow with both sides, This is also important. It means that P implies Q and Q implies P. Effectively, this is the same thing as saying P implies Q and Q. Oops. Just delete that. And Q implies P. Right? And in some other context, you may call it if and only if. Or you may have seen, so these are equivalent, so these are also equivalent to this. Another equivalent of this statements is if. Okay, so if you say P if Q, or P if and only if Q, that means that if P then Q and if Q then P. When you end up with a mathematical statement of this nature that you need to prove, then you have to prove both ways of it. So to prove P if and only if Q, here you have to do two things. One, prove P implies Q, and then two, prove Q implies P. Right? So you have to, when you end up or encounter a bidirectional implication and you want to prove it, then you have to effectively show both ways of these statements. When we work with Boolean logic and Boolean values, most of the time it would be helpful, especially when you have a small number of operations that you're doing, or rather a small number of operands that you're dealing with. You want to you use truth tables, and it simplifies our way of looking at kind of working and understanding what's going on with our operations. But most of the time, actually, we don't rely on using truth tables, because if you have more than 4 or 5 statements that you're trying to work with, then your truth tables become prohibitively large, and so you won't be able to use them anyway. And we would have to rely on other means of building on and deducing the truth of statements. But generally speaking, truth tables lay down your basically work in a tabular format, just like what we did with the functions. On one side, you have your input operations. Let's say that we have 2 elements, P and Q. And what we're going to do is that we're going to list all the combinations of true and false values for P and Q. So P and Q both could be false. P could be false, Q could be true. P could be true, Q could be false. And P and Q both could be true. This will get me all the possible combinations I want. Now you can easily see that if I have another operand like R, then these would require 8 entries. If I had 4 operands, then it would require 16 entries. If I had 5 operands, then it would require 32 entries. So if I had n operands, then the truth table needs 2 to the n entries. Okay, that's one of the reasons I said truth tables are not, generally speaking, useful, except for establishing some basis of what truth and falseness of a combination of statements are, and then taking it from there. So for P, for the not P, right? So not P, remember, it negates the value of P, so it will be TT, sorry, and then FF. Okay, so when P is false, not P is true. When P is true, not P is false. P and Q, it's going to be true when both are true. So only for the last entry it's going to be true. So if either one of them is false AND is going to be false, and if both are false, then AND is going to be false. P or Q, of course, it's going to be false when both are false, otherwise it's going to be true. And then P, X or Q is going to be true for when you only have one of them that is true. Otherwise, exclusive OR is going to be false. P implies Q is going to be, so when P is false, it implies truth. So this is going to be true in this case. When P is true but Q is false, this is going to yield the false statement, and truth also implies true, so this is going to be true there. And then so these are effectively, oh, and the equivalence is going to be true when both are false, true when both are true, and false when one is false and the other one is true. Right? So this is basically the truth table. Now, if I wanted to calculate the truth of something like this, P or Q and not P implies Q, then I could actually do something like this. So extend my truth table, right? So P or Q is here, and this is the truth of it. Then not P implies Q, so then not P implies Q would be false, false, true, false, and then AND of this guy and that guy will be false, 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 true, false, false, true, 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 and true, false, false. So see, I could now use the truth table for just two elements to deduce the truth of P or Q and not P implies Q, which would give me this. So I would know that this statement is going to be true if P is true and Q is false. Otherwise, the statement is false, right? So then this means that this statement is true when P is true and Q is false. Okay, so that's how you use truth tables. There's a special property that the AND and OR possess, which basically kind of sort of relates to what multiplication and addition in the arithmetic arena have with relation to each other, and that's distributive law. The thing is with the arithmetic, the distributive law only works so that the multiplication is distributive over addition, but not the other way around. The distributive law applies to both AND or operands. So if you had an operation like this, P or Q and R, then you could distribute OR over the ANDs. So it would be equal to P or Q and P or R. Same thing with the distribution of AND over OR. So if you have P and Q or R, then it means it's the same as saying P and Q or P and R. So that's a distributive property of the Boolean operators. Okay, now that we've talked about preliminaries, let's take a look and discuss how we can go about and work with the kinds of mathematics that we will be doing in this class. So in order to get to this, let's define some terms. Of course, we have been doing some defining terms, so why not some more? So we start with definitions. Why not? We're defining definitions. So mathematically speaking, a definition is what describes an object or a notation that we use. Definitions could be simple, such as a definition of a set, effectively a list of elements belonging or having certain properties, and that groups them. Or it could be a complex definition, such as a definition of security in a cryptographic system. And later on, as we go on, actually, one of the first things that we get into working with is defining automata, especially a finite automata. And so you'll see how we can lay out definitions that are precise. In fact, what you do defining an object is, however you do it, be very, very precise, because from this point is where you can get going with your mathematical statements. So defining objects must be as clear and concise as possible. That what are the properties that that object possesses, that then you could be working with building mathematical statements on them. So after you have defined your objects and notations, then you will start working with mathematical statements and making mathematical statements about them. Usually these mathematical statements express certain properties that your objects have. For example, such and such combinations of numbers, the sum of them yields a positive number or an even number, right? So mathematical statements basically talk about some properties about the objects that you've built. So it's needless to say that mathematical statements, just like definitions, must be very, very precise as well. There is no room for ambiguous statements. I mean, statements may be complex, may be multi-part statements, but there's no room for ambiguity in the statements. From this, you will be able to derive a convincing logical argument that a statement is true or is false, for that matter. And that is what is called a proof. So effectively, a proof is a logical argument about the truth of a statement beyond any doubt. So the mathematical proofs don't rely on 90% of the time, or over the last 300 years, such and such statement has been shown to be true or has not been shown to be false, therefore it's true. These things don't fly mathematically. So in mathematics, you have to go step by step by step, and as a result of that, you will have to build context. You would have to build statements that then you can basically put them together to derive your proof mathematically and soundly. And actually, in fact, I will try to show you a couple of times in this class that we want to prove a certain kind of statement, and then from the kind of toolboxes that we already have, we are unable to drive that. So then we have to make a detour, build a new notation for ourselves, build a new concept for ourselves, and get from there and try to solve our problems. So or make our mathematical proofs precise and accurate. So that's one thing that we need to be aware of. That's what a proof is. A proof is a convincing logical argument beyond any doubt about the truth of a statement, or the falseness of a statement, for that matter. Sometimes, as I said, it would be very, very hard to establish truth. Sometimes it takes centuries for even an entire field of mathematics to develop to be able to prove a statement. And so some statements are actually there that they have not been proven by anyone, but we are reasonably sure that these statements are true. It's that nobody has been able to successfully prove them. These statements, we call them conjectures. And so those are very high order mathematics, and they're to prove that statement, those conjectures, that there may be a need for a brand new branch of mathematics that will be able to handle that kinds of things. So that's that. There are kind of other terms related to proofs and related to theorems. Is that in fact, actually, I think I skipped defining theorems. Theorems are statements that have been proven to be true. So once you have a proof for a statement and it is proven, then it's called a theorem. So that's theorems, and the ones that are not proven, statements, but you're pretty sure they will be proven at some point, we call them conjectures. And as I said, along the path, the way of designing a proof, we may actually end up proving smaller kinds of statements or related statements that then we can use to prove our theorems. We call those things lemmas. So a lemma is a can think of it as a mini theorem. And then when you prove a theorem, it may be applicable to related statements. There are some statements, once you prove some things, that it would follow naturally. A couple of other statements about other objects that may share certain kinds of properties. We call those statements corollaries to the theorem. So for example, let's say that if you prove a theorem about such and such operation being closed, or rather such and such domain being closed over such and such operation, and then if you have another operation that's kind of related, reasonably close to, then it would follow that it would be closed over this other operation as well. So that would be a corollary to our first theorem. So those are the concepts that we have here. Now, how would you go about finding proofs? I wish I had the answer to that, and unfortunately I don't, and nobody does. There is really no way to build and write an algorithm to produce proofs. In fact, over the last century, there have been countless mathematicians who have started this expedition, and this is actually proven that there is no machine or algorithm that could prove or disprove a mathematical statement, or rather a theorem, or find a proof. It cannot be done. We have tools and techniques to be able to produce proofs, but any given statement needs its own branch of mathematics and its own set of tool sets and techniques to go about proving it. However, I will be talking about a couple of ways, a couple of kind of techniques, a couple of you can call them types of proofs that would be helpful, and they're applicable. The type applies to several different areas in mathematics, but really there's no recipe for producing proofs. There are a couple of things that would help us to go about and work with statements and try to prove them. Examine the statement when you're giving a statement to prove, or for example, if the problem on the homework or the midterm or the final says prove that such and such, or show that such and such, you have to actually prove it. It doesn't mean that you can just pick a couple of examples and just show the example and say, oh, it is true for this, so then I showed you. No, when we see statements like show that a statement, you must prove it. To be able to get to the proof, first off, go about and examine the statement. Do you understand the statement? If you don't, just read it carefully. Try to look at all the different aspects of the statement. Is it a multi-part statement? If for example, if a statement that says show that such and such if and only if such and such other thing, that is a multi-part statement. You have to prove both directions. You have to first start with this assumption and prove the other side is true, and then go the other direction as well and prove both sides, both ways of these statements. I'll actually, in fact, in the next slide I'll show you one of these examples. Multi-part statements. And then do a couple of examples. Sometimes when you work with a couple of examples, draw them, certain patterns emerges out of the examples that you're showing that might point you towards the path or towards the direction of an actual developing and building an actual proof. Another way is to, when you see a statement and you want to show it's true or even it's false, try to find counter examples. Counter examples are the examples that don't fit. For example, let's say that I want to say all square numbers are, or the square of an an odd number is odd. So if I wanted to show that, just try to find counter. Although this statement is true, I can prove it. But try to find counter examples for it. When you try to find counter examples that disprove what the statement is saying, if you find one, good. You just proved the statement false, which means that you produced a proof. It's just the other way of proof. But if you fail to find a counter example that makes that statement crumble, then you might find how to prove it. Certain patterns might emerge while you're trying to find a counter example that points you towards how to prove that statement. Other things to do is, of course, be patient. If you couldn't produce the proof or it didn't work out the first time you tried it, just leave it, think about it, let your unconscious mind work on it, and then come back to the problem. Be neat. You might need to draw things, you might need to kind of write statements, put things together. So try to be neat and be very concise to be able to get to the bottom of the proof, and sloppiness will effectively get in the way. So that being said, I want to show you two mathematical statements, and I want to prove these two statements. So the first example says that prove that the negation of the disjunction or union of two sets is the conjunction of their negations. In fact, actually, this should be intersection. So my first error in this course, and you may begin laughing at me. So if you do union AB and then negate it, it is equal to intersection of not A and not B, or complement of A and complement of B. It's actually easy to see it in the Venn diagram, but Venn diagrams is not proofs, but it could show us or help us see. As I said, just draw examples and so forth. So if I have A and B, so their unions is that. This is their union, and the negation of it is all these areas that are outside here. Okay, so this is not of A union B, or complement of A union B. Now, if I do this, okay, then if you look at the, so this is my A and this is my B. So the not of A, or the complement of A, is going to be everything that's not inside A. So that will be all these areas, right? So all these areas will be not A. So this is going to be not A, the complement of A. Then complement of B, if only I could get to my pen color, there you go. So complement of B is going to be all these areas that are not in B. So that's going to be, these guys are going to be not in B, right? So these are going to be not B. And if you find the intersection of these, it's going to be there. So this area is going to be the intersection of not A and the intersection of not B. Okay, so with Venn diagram I can see it. Now I need to prove it. So these two effectively, visually, I showed that these two are the same. So this area is equal to the other area at the bottom here. But I need to prove it. So let's go about and produce this proof. Okay. So what I would like to prove is this statement, that if I have two sets, A and B, are sets, and then I want to show that A or B complement, or A union B complement, is A complement intersection with B complement. As I said, be careful about what you're reading here. This statement is a two-part statement. In fact, if you remember when we talked about sets and equalities of sets, we said that two sets are equal if each one of them is the subset of the other one, right? So in order to make this proof, to prove this, I would have to prove two statements. So I need to prove two statements. Prove that A union B complement of it is a subset of A complement intersect with B complement. So this is proof number one. And then also I need to prove number two, that A complement intersect with B complement is also a subset of A union B complement. So I need to make these two proofs to be able to show that. Now, to build this proof, I need to rely on definitions and statements. So let's do a couple of definitions. So definition number one is the definition of subset. What is a subset? Okay, so we say A is a subset of B, and we define it like this. This is a definition. If for every x in A, x is in B. So this is the definition, a very basic definition about one set being the subset of the other. And remember, we defined this in the last unit definition of a subset. So if you have two sets A and B, we say set A is a subset of B if every element of A is also an element of B. So from this, I can actually start working. Also, I need another definition here, and that's the definition of complement. So we also defined the complement last time. It was the set of X such that X is not in A, right? So these two definitions actually help me now. A subset definition and a complement definition help me do my proof. So let's start with proof of the direction one. I want to say and prove that the complement of union of A and B is a subset of the intersections of their complements. So how am I going to do this? I'm going to look at every element that belongs to the complement of the union of A and B, right? So if I have an element that is in the complement of union of two sets, so let me draw it here for you to see. So if you have the union of two sets, which is this, its complement is everything that's not in it, right? So its complement is all these red areas out here, right? Which means that if an X is in the complement of the union, then it's not in either one of those two, right? So if X is in the complement of A union B, then X is not in A, and X is not in B. That's how the X ends up in the complement of their union, because if X were in A, then it would be in their union, If X were in B, then it would be in their union. So for the X to be in the complement of their unions, it should not be in either one of the two. So it's not in A, and it's not in B, right? Now see from the definition of the complement here, if X is not in A, then X is in the complement of A. So from here, then I deduce that X then must be in A complement, and the same logic applies here. X must be in B complement. See, if X is not in A, then X is by definition in the complement of A. And if X is not in B, then X by definition is in the complement of B. Now, what is the meaning of intersection? The meaning of intersection, so A intersect B by definition is all the X such that X is in A and X is in B. Right? So now just replace A and B with A bar and B bar, we get the complement. So according to this transition then X belongs to A bar and intersect with B bar. Right? So exactly this definition here helps me. So definition number 1 helps me here, right? According to 1, and definition number 2 helps me here. So according to definition number 2, then X belongs to A bar intersect B bar. Okay, now what happened here? See, now here, therefore, we started with every X from A union B bar, and we found out that X is in A bar intersect B bar. Voila! Number 3 here. Definition number 3 is the definition of the subset. So from here then, we know that A union B bar is a subset of A complement intersect B complement. Therefore, I proved one direction. Direction number 1. Okay? Now let's look at the direction number 2 here. Direction number 1. Let's call this D sub 1, and then D sub 1, and then D sub 2. Now let's look at D sub 2. To prove D sub 2, I want to show that every element of A complement intersect B complement is also an element of A union B complement. So what I'm going to do is then I'm going to look at every X that belongs to A complement intersect B complement. According to the definition 2 from here, if X belongs to A intersect B, then X belongs to A and X belongs to B. So then according to this definition, then X belongs to A complement and X belongs to B complement. Now I'm going to look at the definition of complement, number 1. So according to definition number 1 here, since X is in A complement, then X is not in A. So X is not in A and X is not in B. Sorry, this means get rid of the complement. So X is not in A and X is not in B. So if X is not in A and it is not in B, that means that X belongs to one of these red areas here. So from here then, I know that then X will belong to the complement of their union. Right? Because if X is not in A and it's not in B, it will not be in the union of them, then it will be in the complement of their union. This proves the second direction, because then here what I did is that I showed that for every X, or for all X, that is in the intersect of the complements of these two guys, then here X belongs to the complement of their unions. And this proves direction number 2 for me. And then from proof of 1 and proof of 2, I know that so proof of 1 states that the complement of the union is a subset of the intersections of the complements. So proof number 1 that says that. Proof number 2 says that the intersection of their complements, so A complement intersect B complement, is a subset of the unions. That's proof number 2. And these two prove that A union B complement is equal to A complement intersect B complement. And this is the proof for my statement. It was an easy statement, but in order to prove it, I had to prove 2 directions. Direction number 1, which I did up here. So that I did direction number 1, and this I did direction number 2. And then the combination of the 2 directions give me the actual proof down here. Alright, now next we're going to go and do the proof the second statement. And just for the fun of it, in this second statement I put it in English terms, and so I say show that for every graph G, the sum of all degrees of the nodes in that graph is an even number. Remember, the degrees of a node was or is actually the number of edges that each node has. So let's actually take a look at a graph. So let's draw a graph with 2 nodes, node 1 and node 2. So if I connect these 2 nodes, then the degree of node 1 is 1, degree of node 2 is 1, because each of them has 1 node. So the sum of the 2 degrees is 2. It's an even number. Let's draw another node and connect an edge to it. So node number 3. So now degree of node number 1 is 1, degree of node number 3 is 1, and degree of node number 2 is actually 2, 1, 2. So the sum of these degrees, so the sum of I degree of each node is 4, which is an even number. The actual proof for this, if I actually were to really build a proof, I would use proof by induction. And in fact, I will show this proof by induction later on to you. But one way to look at it is that every time you add an edge to a node, so every time you add an edge, then what you're going to do is actually you're adding an unordered pair, d sub I and d sub j. So what that means is that you add an unordered pair to your graph. And since this unordered pair has 2, so let's call this guy d sub ij for that edge that you added to the graph. So d sub ij is actually one edge, but it adds 2 to the total degree, right? Once to the degree of d sub I, and once to the degree of d sub j. So then therefore every time an edge d sub I comma d sub j is added, it adds 2 to the degrees. And therefore every time it adds a number 2, an even number to the sum, so therefore the sum of the total edges, the total degrees in a graph, will be effectively an even number, because every edge adds 2 to the degree. So if your graph has n edges, so if your graph, for example here, if a graph here has 2 edges, then the total degrees is 2 times 2. So if a graph has n edges, then the sum of degrees is equal to 2n. And that proves your statement. Now this is a sloppy proof, I agree, but it's proof nonetheless because it's beyond any doubt. But to formalize it and to really nail it, I will show this by proof by induction later on when we talk about proof techniques, and proof by induction is a very powerful technique, and in this case you can see that it requires building something, and so proof by induction precisely does that for us.